Hi folks, this is Nat, and this is going to be a video lesson on combinations and permutations, which can be incorporated into the probability work that we sometimes do, particularly more complex questions. So we're going to start with the difference between combinations and permutations. We've been using combinations, as many people do, kind of actually incorrectly. There's a big difference between combinations and permutations. Combinations, when we talk about them strictly speaking, order doesn't matter. So in terms of combinations, if I have thing 1, thing 2, and thing 3, that's no different than having thing 2, 1, and 3, or thing 1, 3, and 2, or any of the different ways that I could write those three numbers. Permutations is the opposite, where order does matter. So in permutations, 1, 2, 3 is a unique and different thing from 2, 1, 3. So one of the jokes that mathematicians like to tell is that a combination lock should really be called a permutation lock, because when I do one of those master lock things with the numbers, it matters a lot what order I put the numbers in. If the combo is 21, 23, 34, 18, I can't put it in a different order. So order matters, therefore it should really be called a permutation lock. So some examples of this, 10 people are running a race. There will be a gold, silver, and bronze medal awarded. The first question we might ask ourselves in determining is it a combination or is it a permutation is, does order matter? And when we start talking about gold, silver, and bronze, hopefully you recognize that, yeah, order matters here. At least it probably matters to the person who got silver and bronze and not gold. So in this case, the number of permutations, the number of ways that people can fill those three slots, order matters a lot. And the way we'll calculate those is by thinking about how many people can fill those slots. So gold is obviously the person who finished first, and there were 10 people in the race, so there were 10 people available to fill that slot. Once that first person crossed the finish line, there were only 9 people remaining who could fill that second silver slot, and 8 people after that to fill the bronze slot. So the way we determine the number of permutations is by taking those and multiplying them together. The 10 people then, or times the 9 people to get silver, times the 8 people to get, who could have gotten bronze, gives us a grand total of 720 different permutations for how those gold, silver, and bronze slots could be filled. And again, this is permutation. So person 1, then 2, then 3, first, second, and third is going to be different than person 2, then 1, then 3. So we're counting all these different arrangements of people because it's a permutation, because order matters. When we talk about this example, 10 people are in a charity chili cook-off. The top 3 vote getters will each receive a $50 gift card. Here we've got a slightly different scenario because realistically, like maybe I care if I'm the highest vote getter or maybe I don't, but my prize is going to be the same. So if we're just saying like how many different ways can we distribute those $50 gift cards, now we're in a scenario where order doesn't really matter a whole lot. I've got 10 people who could fill the slots, but if I'm person 1, 2, and 3 filling the slot, I don't care whether person 3, 2, or 1, or person 1, 3, 2. We're all just going to get $50 gift cards, so it doesn't really matter much. So in determining the number of combinations, it's actually an extra step. We're going to start off doing the exact same thing, which is we need to think about how many permutations are there. Same idea as before. I have 10 people who could get the first $50 gift card, and then 9 people, and then 8 people for that same 720 people. But now I need to find an efficient way of removing all the repeats of, say, like 3, 2, 1, 1, 2, 3, 3, 1, 2, 1, 3, 2, 2, 1, 3, or 2, 3, 1. And it turns out there's a really easy, efficient way to do this. If we think about the number of people who are going to be sharing those things, which is 3, we can say, well, there's 3 people originally, and then there are 2 people once that first person's decided, and then there's 1 person to finish off, which means that there are 6 repeats, and we actually did them over here. There's 6 repeats for every combination. So if we know that there's 720 permutations and 6 repeats for every combination, we can just split the 720 into 6 pieces. 720 divided by 6 in this case equals 120 actual unique combinations of 3 people. So combinations in the real sense are very much like permutations with an extra step. We have to figure out how many extra or repeats there are and then remove those. And one of the tools we have to make this fast is a mathematical notation called a factorial. And that exclamation there is actually a math joke because factorials are done with exclamation points. So when you see 4 exclamation point, what that means in mathematical terms, or 4 factorial, is that you're going to take 4, starting with the number 4, and multiply all the way down from 4 by whole numbers to the number 1. So 4 factorial is 4 times 3 times 2 times 1, or 24. If you see 5 factorial, it's the exact same thing, except it starts at 5. 5 times 4 times 3 times 2 times 1, which is, I believe, 120. So anyhow, that's what a factorial means, and it's sort of a fast way, particularly if you have a calculator, for calculating some of these things that we're talking about. If we go back and look at this idea of 10 times 9 times 8, we could have expressed that idea in example 1 as 10 factorial. Of course, that includes a 7, 8, 6, 5, 4, 3, 2, 1 we don't want. So what we do is we say 10 factorial over 7 factorial, or divided by 7 factorial, to remove all those parts that we didn't want. And that's how we calculate permutations. The top value is the number of choices we start with, while the bottom value is all the stuff we want to remove. Typically, if I was to write this into an equation, I would write it as, say, permutations factorial, the number of permutations I'm interested in, divided by the permutations I don't want. So permutations minus the number of things I have factorial, which is not the official equation, but it's pretty close. When we look at combinations, it's the same idea. Same as before, we start out with that idea of 10 times 9 times 8, or 10 factorial, but we don't want the 7 factorial. We want to remove the 7, 6, 5, 4, 3, 2, 1, and we also want to remove the 3, 2, 1 from the combination of 3 things, or 3 factorial. So I'd write that 10 factorial over 7 factorial times 3 factorial. And I could put those into a calculator to make calculating those things very quick and easy. So now we can apply that to probability really quickly. If I want to know what's the probability of getting a red, green, and yellow in any order from this bag of marbles, what I'm really asking is for permutations, because when we think about probability, probability cares about order. The probabilities are based on order, among other things. So I care if it comes out red, green, yellow, because that counts as an option or a permutation. So does red, yellow, green. They're not different. So we can use factorials or permutations to help us calculate probabilities. I can say if I pull 3 things, I know that there's 10 things originally in this bag. So I know that there's 10 times 9 times 8 permutations that can come out of this bag. or the same 720 we've been dealing with before, 720 permutations. So now I know all the different things that can happen. There's 720 different permutations of 3 things that can come out of this bag. And now I'm interested specifically in how many of those are 1 red, 1 green, and 1 yellow. Well, if I want to go in a specific order, red, green, yellow, it's a 5 times 3 times 2 chance that I go red, green, yellow specifically, which is 30 ways of getting red, green, yellow. But I might in this case notice, well, in this case I don't care about order, so I would also accept yellow, green, red, or green, yellow, red, or a number of other combinations, permutations again, I guess, of those 3 colors. So how many different permutations do I have to account for? In this case, I can find that by saying 3 times 2 times 1 for the 3 different colors I'm looking for, or 6 permutations of red, green, and yellow. So I know that each of those permutations has 30 ways of getting there. There's 6 of them. So if I multiply those together, I have 180 ways of getting some permutation of red, green, yellow. I can take that 180 out of my 720 total permutations, and that's my probability of getting 1 red, 1 green, and 1 yellow. And I could reduce that, but that is basically how, one way at least, that combinations and permutations can be used. So here's some practice problems you can try out. They both have to do with this bag of marbles labeled 1, 2, 3, 4, 5. You can think first about how many unique combinations of 3 marbles are possible. And then you can think about, if you draw 3, how many permutations are possible. So we'll really kind of dig into that. Good luck.